Chapter 4 The Diode Circuits. There are 12 sessions in Chapter 4. Section 1, that's the half-wave rectifier. Section 2, transformer. And then we're going to cover the full-wave rectifier and a better rectifier called the bridge rectifier. And then we have Section 5, the choke input filter, followed by the capacitor input filter. And then we cover the peak inverse voltage and the surge current. After that, we talk about the other types of power supply. And the 9, troubleshooting for the diode circuits. And then we cover clippers and limiters, clampers, and then voltage multipliers. Without further ado, let's begin with Section 4.1, the half-wave rectifier. Before we're learning the rectifier circuit in depth, let's talk about the reason we are learning it. This is a block diagram of a regulated DC power supply. It shows the main stages of converting AC power into stable DC power. This is how it works. The input AC signal is entering into a transformer. The transformer changes the AC voltage level. For most appliances, the input signal is very large. It is 120 volts in the States, and that's the room and square voltage. And for most appliances, it cannot handle this much voltage, with transformer to step down the voltage to a lower voltage level that appliance can operate. And then that signal is entering into the rectifier, where a rectifier converts AC into pulsating DC, which means the signal is like DC but is made of pulses. This signal is being forwarded to the filter. The filter is used to smooth the pulsating DC and reduce the ripples. And then we have a regulator to maintain a nearly constant DC output voltage. And at the end, this nearly constant DC sends it to the load resistor. The electronic device that's the process is the power supply. Power supply that connects the outlet to your laptop. That input is alternating current, and the output is DC signal. This chapter will mainly focus on the rectifier circuit. But in order to learn how to use the rectifier circuit, we also need to use transformer. Section 4.2 is about transformer. Here we have a very simple diode circuit. There is a diode, and this diode connects to an AC source. The other side of the diode connects to a current limiting resistor, RL, and this forms a simple half-wave rectifier. Now let's analyze this half-wave rectifier. To make our study easier, let's begin with an ideal diode, which means there's no knee voltage. We don't need 0.7 volts to activate it. As long as there's current that flows in the same direction of the diode that's pointing to, the current pass through. We know the sine wave source, the Vs, produce a sine wave. At certain time, the signal is positive, and after a certain time, it becomes negative. And this pattern is being generated repeatedly. The peak value of this sine wave, let's call the Vp in. That's the peak voltage of the input signal. So the lower peak is negative Vp in. When this sine wave goes through the diode, only the positive portion can go through it, because that's the forward bias. And then the negative side of the current won't go through it. This is when the current tries to go in the opposite direction of the diode, and the diode blocks it. So on the output side, we'll only see the upper portion, the positive side of the sine wave, and then the negative side is being erased, removed. We learn how the half-wave rectifier signal is being generated, the reason behind it. Now let's take a look at important quantities and formulas we need to know. The first one is called the DC value of a sine wave. This is similar to the average value of this half-wave rectified signal. So what I mean is, imagine a signal with a DC voltmeter. The reading will equal to the average value of that signal. So in the basic courses, the DC value of a half-wave signal is derived. This requires using calculus, but let's skip that derivation and just focus on the formula. The formula is that VDC equals to the peak voltage of the sine wave, the original input sine wave, divided by pi. So you can also write this as Vp, whatever the peak voltage, divided by 3.1415926. If you use calculator and enter the 1 over pi, we get a decimal that equals to 0.318. So the second expression, just another way to show the same formula, that can be rewritten at 0.318 times the peak voltage. As you can see, if the peak voltage is Vp, the average of the half-wave rectified signal is rarely 31% of that peak voltage. Now let's take a look at the frequencies between the input and the output waveforms. So let's look at the input waveform. We know the sine wave goes up and down. If we use the word hue to represent the upper portion, and then the basin represent the lower portion of the sine wave, and then we compare that with the output, there is a hue, but we have a flat ground. The flat ground replaces the original basin area, but the duration is same. Both have t to complete one cycle. The main difference is for input is go up and goes down, and then for the output is go up and go straight line. So we conclude that for half-wave rectifier, the output signal's frequency, F out, equals to the input signal's frequency, F in. When you are troubleshooting, you can use the ideal diodes to analyze a half-wave rectifier. It's useful to remember that the peak output voltage equals to the peak input voltage. On previous study, we used the first approximation of the diode to learn this rectifier circuit. But most of the time, we need to get a more accurate answer, and it's the time we need to use the second approximation. For second approximation, we don't get a perfect half-wave voltage across the load resistor because of the barrier potential. The diode does not turn on until the AC source voltage reaches approximately 0.7 volt. When the peak source voltage is much greater than 0.7 volt, the load voltage will resemble a half-wave signal. For example, if the peak source voltage is 100 volts, the load voltage will be close to perfect half-wave voltage because the 0.7 volt is too small compared to the 100 volts. It can be neglected. However, if the peak source voltage is not that large, for example, it's only 5 volts, the load voltage will have a peak voltage of only 0.3 volts, and we shouldn't ignore this 0.7 volt, especially that peak source voltage is not that large. When you need to get a better answer, and use following derivation. If you use the second approximation to study the half wave, so output peak voltage equals to the input peak voltage, and then remove that 0.7 volts from the diode. Power companies in the United States supply a nominal line voltage of 120 volts. This is not the peak voltage. is the root mean square voltage, and a frequency of 60 Hz. The actual voltage coming out of a power outlet may vary from 105 to 125 voltage, depending on the time of the day, the locality, and other factors. Line voltage is too high for most of the circuits used in electronics equipment. This is why a transformer is commonly used in the power supply section of almost all electronics equipment. The transformer steps the line voltage down to a safer and lower levels that are more suitable for use with diodes, transistors, and other semiconductor devices. Most designers will make sure that the buck resistance is much smaller than the Thevenin's resistance facing the diode. Because of this, we can ignore buck resistance in almost every case. If you must have better accuracy than you can get with the second approximation, you should use a computer and a circuit simulator like Multisim.